Listen up. All you really need to know about solving exponential equations using the one-to-one property is this exact statement right here. 3 raised to the x equals 3 squared. Now, when you think of that, you might say, well, that's very obvious. Like x has to equal 2. And again, you're right? I mean, 3 raised to what number equals 3 raised to the second power? It makes only sense for x to equal 2. So when we're solving exponential equations, the first thing we always want to do is see if we can create this relationship. Sometimes the relation is already set up. Sometimes it's not. So in this video, what I want to do is work through a couple different examples where we can use this relationship and this understanding to solve exponential equations. But that's only going to work if you understand this. You have to understand this first. And why this is so important is because if we can get an equation where the bases are exactly the same and we have an exponent equal to an exponent, nothing else, then we can just set the powers equal to each other. So even in an example like this, you notice that my bases are the same. You notice I have an exponent equal to another exponent. So again, even though my powers might not be as simple for me to understand what the answer is, I can still just say that my power is going to equal to my power. Now I can just use my inverse operations to go ahead and solve for x. Now you can see that the value that's going to make this equation 2 is indeed going to be x is equal to 6. So now hopefully you recognize, I don't care what the exponents look like, as long as you see the bases are equal to each other and you have an exponent equal to an exponent, just set the powers equal to each other. Now what about in an example like this, where the bases are not the same? Again, our whole goal here is to get this to be as 3 as the base on both sides or a 9 on the base on both sides. Now the interesting thing I recognize about 9 is I can rewrite 9 as a 3 squared. And if I write it as a 3 squared, then guess what is my base? 3. So therefore I can just rewrite this equation as a 3 to the x equals a 3 squared raised to the x plus 1. Now, remember, using the power rule of exponents, I can now go ahead and rewrite this as a product of my two powers. So 3 times, or 3 raised to the 2 times an x plus 1. Now, notice the little trickery I did here. I rewrote this with using parentheses because the 2 is not being multiplied by x. The 2 is being multiplied by the x plus 1. So now you can see we have this original relationship that we are looking for. 3 raised to the x is equal to a 3 raised to the 2x plus 1. Same bases, only one exponent on each side. So now I can just say x equals a 2 times x plus 1. Now go ahead and apply my distributive property and I get x equals a 2x plus 2. And now you can just go ahead and solve. And you can see here an x is going to equal a negative 2. Now, sometimes it's obvious to recognize 9 as a 3 squared, but what about when you have fractions? Now, in this example, you can see that I have a fraction as my exponent of my base. And I always like to joke with my students, nobody likes fractions, right? Let's just kind of be honest. Nobody really likes fractions. Maybe there's a couple of you out there that kind of enjoy the torture that sometimes fractions can bring. But typically when I'm viewing a problem and I see fractions, the first thing I want to do is get rid of those fractions. Now, hopefully you remember on the rules of exponents, I can rewrite a number using negative exponents. Now, if I rewrite a 1/3 as a 3 raised to the negative first power, that's going to give me a 3 as my base, not a 9. So what that means is I'm also going to want to rewrite a 9 as a 3 squared. And now you can see, again, what did I just do? I set the bases to be exactly the same. And now, using the power rule of exponents, I'm just going to multiply my numerators. Again, in this case, I'm not going to show my work of using parentheses. I am just going to hope and assume that you don't make the mistake and you insert parentheses yourself and apply the distributive property. Now I'll just set my powers equal to my powers and I get a 4x is equal to a negative 2x plus 1. Now just get x's to the same side and solve. An example like this, it might not be obvious at all to look for 3 as the bases. So again, what we want to think about is that bases are not exactly the same. So therefore, in this example, right now, we are kind of stuck. We want to get the bases to be the same. And another way to kind of think about that is we want a number raised to another number that's going to equal a 81 as well as a 243. That number that's being raised has to be the same. So you could think of 2s, right? You could think of 3s, you could think of 4s, you could think of 5s. Now, obviously, as the theme of this video, we've been looking into 3s. And so far, we've only covered a 3 raised to the second power. So let's just go and expand upon that a little bit and kind of see 3s raised to higher powers. Aha, and just with a little practice with your number 3s, you can see that I can actually rewrite 81 as a 3 to the 4th power, and I can rewrite a 243 as a 3 to the 5th power. Now again, even if you had no idea what I was doing, like it just takes a little bit of practice, and you can see on the side, I was able to come up with these values. But again, our main idea, what I want you to know about this is getting the bases to be exactly the same when you have an exponent equal to another exponent. So now I'm just going to rewrite 81 as a 3 to the 4th power, and I'm going to rewrite 243 as a 3 to the 5th power. Now, again, I'm just going to apply my distributive property. Again, I'm going to insert the parentheses so you don't make the same mistake that I and many other students will make if you're not being careful. So now I just set my 4x plus 1 equal to a 5 times x minus 7. Now just apply distributive property and get your variable onto the same side to solve. So there you go, ladies and gentlemen. The answer you can see in this example is going to be x equals 39. Hopefully by now you recognize that 3 raised to the x equals 3 squared, then x equals 2. But there's a couple things I want to talk to you about. What about now if I make some changes? Is this relationship still going to work? What if I have 3 to the x equals a 3 squared plus 1? Well, guess what? X no longer is going to equal 2. What about if I have a 3 raised to the x equals a 2 times a 3 squared? Guess what? X is no longer equal to 2. What about if I have a 3 raised to the x equals a 4 raised to the second power? X is no longer 2. So it's very important to understand that this relationship only works when you have an exponent equal to another exponent with its basis being the same. Whenever we start adding values on one side or the other, or we change the bases, we can no longer use the one-to-one property. That's why I created this video right here. If you need more examples on the one-to-one property, check the examples down below, or check out the next video I have for you here. Cheers.